Good morning to all the students. In this session, we are going to discuss a concept called the primality testing. This particular concept is used to test whether a given number is prime or not. We have n number of algorithms to check whether a given number is prime or not. So in last session, we have seen the last concept, which is called as generating primes. What are the two formulas that we have used for generating primes? One is Mersenne number and the second one is the Fermet number. Right. So these two authors has proposed two formulas. So the Mersenne number is MP is equal to 2 power P minus 1. And the Fermat number is given by the formula Fn is equal to 2 power n minus 1. So these two formulas are used to generate the prime numbers. But the problem with these two formulas is they are able to generate the primes, but at one point of time they have generated a number which is composite. The thing is that this MP and Fn, both of them has to generate only the prime numbers. So the others thought that these are the formulas that can well construct or that can give a prime number. But later when they have implemented this, they have generated the prime numbers using these formulas. They are not able to generate all the primes. Why? Because if you see the Fermat number, the F5 is given by 2 power 5 minus 1, that is 2 power 32 minus 1. It's a very large number, forget about this. So this number, they thought of it as a prime number, but this turned to be a composite number. So because of this problem, the Fermat and Mersenne's number had failed to produce large prime numbers, right? So small numbers like F1, F2, F3, F4 are very much developed by this, and they are correct that they are prime numbers. But when coming to generating the large prime numbers, they failed. The Mersenne number as well as the Fermat number, they failed, right? But the concept here is, in cryptography we require large prime numbers. We require large prime numbers. We need to generate large prime numbers. So for this reason, what they have done is they have found an algorithm to correctly and efficiently test a very large integer number, right? So this is not the concept of generating the primes. Here what we will do is, we will take a number n, large prime number, and the challenge is to check whether the large integer that we have selected here, this one n, is either a prime or a composite. So the testing of an integer to check whether it is a prime or composite is called as the primality testing. Is it clear?
Yes, sir.
So this primality testing, we have, as I told, that we have lot of algorithms to test whether a given number is prime or composite. But these primality testing algorithms, they are broadly categorized into two categories. One is the deterministic algorithms and the second one is probabilistic algorithms. Right, we have few algorithms under this deterministic, only two algorithms, and we have around 3 to 4 algorithms under this probabilistic algorithms category. So we should know what this deterministic algorithm is, and we should know what this probabilistic algorithm is. So what do you understand by the term deterministic? Any idea? For example, if I say that a girl is so deterministic in achieving her goal, so what does it mean? So she is very much concentrated and she decides whether it is correct or not, right? So only one answer is there, whether she will achieve it or not. But probabilistic means they have some probability of achieving it, and they have some probability of not achieving it, right? So in the similar manner, if you take the deterministic algorithms under this primality testing, the algorithms always gives correct answers. So these deterministic algorithms, they are always outputting the correct answers. Whereas if you consider the probabilistic algorithm, it gives an answer. We'll get an output from this, right? We'll get an output. But this output is correct most of the time, but not always, right? So what are output we get from these probabilistic algorithms? The output will be correct most of the time. That is the reason why we are saying that we are giving the probability that it is going to give the correct answer. This is the probability that the output can be correct, and this is the probability. That means whenever we say the probability of correctness, there always exists the probability of wrong answers also, right? So that is the main difference between the deterministic category and the probabilistic algorithm category. So the deterministic algorithm gives the correct answers all the time, and the probabilistic algorithms, they give the probability of correct answer, and there lies the probability of incorrect answer also, right? So most of the time the answer will be correct, but there are chances that the answer may not be correct. Is it clear?
Yes, sir.
So coming to the deterministic algorithms, as I told that it will always give a correct answer, but the deterministic primality testing algorithm, what it will do is it will accept an integer and it outputs yes or no, whether the given number is prime or composite. So this is how the deterministic algorithms are designed, right? But the problem with these deterministic algorithms is all the deterministic algorithms are inefficient to find large primes that were considered infeasible, right? So they also failed to test whether the large prime numbers that is given as input to the deterministic algorithm, they fail to check whether it is prime or not. Right. So the same problem exists with the deterministic algorithms also, but that problem has been rectified with the probabilistic algorithms. We'll see what are these things we have. Right. Under these deterministic algorithms, the first and foremost deterministic algorithm we are going to discuss is divisibility algorithm. This we have seen in the last session. We'll come back again and discuss this thing. And after this divisibility algorithm, we have another algorithm which is called as AKS algorithm, right? So nothing more to discuss on this divisibility and AKS. We'll see what this divisibility algorithm is. Why? Because we'll be keep on using this divisibility algorithm to check whether a given number is prime. It's a very fundamental algorithm. We can say that it can be a fundamental algorithm, as I told that, but it is inefficient. It is not, it is inefficient, right? So these are the two algorithms which we are going to discuss under the deterministic. Even we don't have any algorithm of this AKS given in our prescribed textbook, so we won't be bothering about this AKS algorithm also. And coming to the probabilistic algorithms, we will be discussing the Fermet test. This is one algorithm we are going to discuss under this category. And then we have square root test, and finally we have Rabin Miller algorithm. So this Rabin Miller, or you can say it as Miller Rabin also, nothing wrong in it, right? These are the two authors who invented this algorithm, therefore this algorithm is named after them, which are called as the Rabin Miller algorithm, right? So we'll be concentrating more on this Rabin Miller algorithm. We'll tell you what is the reason why we are concentrating on this Rabin Miller is it performs, or it gives better performance than any other primality testing algorithm. Even in the probabilistic also, Fermet test fails in some cases, square root test also takes a lot of time to compute the things, but Rabin Miller performance is much better than this Fermet test and the square root test. So that is the reason why we concentrate on this Rabin Miller. We will also see some examples on this Rabin Miller also, right? So please concentrate, it involves a lot of mathematics, right? So is it clear up to this point?
Yes, sir.
And we will end up this session by discussing the recommended primality test. So this recommended primality test is nothing but a hybrid primality testing. So it involves the divisibility algorithm. It's a combination of divisibility and RM algorithm. RM algorithm is nothing but Rabin Miller algorithm. Is it clear?
Yes, sir.
So by this time you might be clear that what do you mean by this primality testing. Primality testing is nothing but the algorithm which takes an integer as a number, whether it can be a small integer or a large integer, and gives the output saying that the given number is prime or composite. And these primality testing algorithms are categorized into two categories, the deterministic algorithm and the probabilistic algorithm. Deterministic algorithm gives the correct answer all the time, and the probabilistic algorithm, they give correct answer most of the time but not all the time. So we have two algorithms under the category of this deterministic algorithm, that is the divisibility algorithm and AKS algorithm. And the probabilistic algorithm, we have the Fermet test, square root test and Rabin Miller algorithm. And finally we will be discussing this recommended primality test, which is nothing but a hybrid. It's a combination of the divisibility algorithm and Rabin Miller algorithm, right? So we'll start our discussion. So this is what we have discussed. Is the screen visible to you?
Yes, sir. Yes, sir.
This PDF document, right? So coming to primality testing, as I told that the Fermats and Messines have failed to create large prime numbers, but the cryptography requires large primes to be generated. So there are algorithms to test whether a very large integer is a prime or composite, right? And they have broadly categorized these algorithms into the deterministic algorithms and the probabilistic algorithms. So the deterministic algorithms always gives a correct answer, and a probabilistic algorithm gives an answer that is correct most of the times but not all the time. So this everything we have covered in the introduction discussion, right? And coming to this deterministic algorithms, what is the input to this deterministic algorithm? It is nothing but a large integer, which is very large, and the output is, it will simply give whether the given number is prime or composite. That's it. Any divisibility algorithm you take, any deterministic algorithm you take, sorry. So the first algorithm which we are going to discuss under this deterministic algorithm is the divisibility algorithm. It's the most elementary deterministic test, right? So in yesterday's session also we have seen one divisibility algorithm, where if you want to find whether a number is prime or not, the first and foremost step what you will do is you will find the square root of n, right? For example, if I want to check whether 71 is prime or not, first of all I have to find, we have seen an example, right? 98. So square root of 98 is, we have to take the floor value. What is this floor value of square root of 98?
9, sir.
9, right? So basically the divisibility algorithm says that we have to consider all the divisors, right? We have to consider all the numbers basically which are smaller than this square root of n. So if any of this number divides this 98, that is n, then we say that it is composite in nature. Otherwise we say that it is prime number, right? So this is the basic divisibility algorithm. They have taken all the divisors which are smaller than square root of n, but later they have modified it. Actually we can say that they have improved it, right, by testing only odd numbers. They have initially taken all divisors and later they have modified it, saying that they have taken only odd numbers which are less than square root of n. This is also less than square root of n, and again they have remodified it, or they have improved it, saying that we can only consider the primes, all the primes that are less than square root of n. So this is what we have discussed in the last session, right? We have taken square root of n and we have taken all the primes that are less than 9. So we have 2, 3, 5 and 7, and we will check each and every prime number whether it is dividing this 98 or not, right? So if any of the number is dividing this 98, then we say that it is composite. So if none of the numbers is dividing this 98, we say that it is a prime number. Clear? Is it clear up to this point?
Yes, sir.
Right. So the primary application, this is what the divisibility algorithm is, right? So forget about everything. You remember that the basic algorithm to check whether a given number is prime or not is you take the square root of the given number and you list out all the prime numbers that are less than or less than square root of n, and you check whether those set of numbers is divisible by 98, the n is divisible by those set of numbers or not. So if any number from the set is dividing n, we say that the number is composite. If none of the numbers is dividing this n, we say that it is prime. Clear?
Yes, sir.
Right. So basically one of the application of this divisibility algorithm is to check whether a given number is prime or not. But coming to the time complexity of this divisibility test, we can say it as the divisibility test also. So the time complexity of this divisibility test is exponential. So this is where the algorithm has failed. Though it is able to check whether a given large integer is prime or not, the time complexity of this algorithm is very high. It is exponential in nature. So for example, if you take an example like this, right? So the time complexity, the bit operation complexity, we can also say that bit operation complexity. Why? Because the bit operation complexity is nothing but we are going to make use of we are going to make use of these algorithms on computers. So we can take it as bit operation complexity. So the bit operation complexity of this divisibility algorithm is given by 2 power nb by 2, where n stands for number of bits, nb stands for number of bits, right? For example, the author has given an example saying that if n is equal to 20, so n is equal to 200 means it represents number of bits. He is asking us to find the bit operation complexity. So how much time the divisibility algorithm is going to take in order to perform this divisibility test on 200 bits, right? So what is the time complexity we have here? What is the formula? 2 power nb by 2. So if I take it like that, so it becomes 200 by 2, which is equal to 2 power 100. So these many bit operations are required for just 200 bits, right? And assume that the computer is operating at 2 power 30 bits per second. Even then, to operate this 2 power 100 bits, we require 2 power 100 by 2 power 30, that is equal to 2 power 70 bit operations. So 2 power 70 seconds is not a simple issue. It's we can say that it is an infinite time, right? It takes a lot of time to compute these things, right? So if you take just 200 bits of operations and the computer speed is around 2 power 30 bits per second, then it is going to take 2 power 70 seconds, which is almost we cannot calculate it. So we can say it as the infinity time, right? So this is the time complexity or the bit complexity that is taken by the divisibility algorithm. Clear?
Yes, sir.
So this is not suitable.
Yes,
why? Because it is taking lot of time and the complexity, bit operation complexity is exponential. This is not that much suitable for large numbers. So there is another category of algorithm. There is another algorithm in this category, that is AKS algorithm, which was developed in the year 2002 by Agarwal, Kyle and Saxena. That is the reason why they have kept it the name as AKS algorithm. Agarwal, A, Kyle and Saxena. And they have developed the algorithm, and the primality testing with polynomial bit operation time complexity is here. The time complexity of this algorithm, AKS algorithm, is big O of log nb base 2 power 12. Right. So if you take the same example of 200 bits, so the time complexity is around log 200 base 2 power 12, which is something around some 13 bit number, 13 numbers we have. Right? It's a very large number. And if you consider a computer that is operating at 1 billion bit operations, that means 2 power 1 billion means what is the 10 power 9, right? So if the computer is operating at this speed, in order to calculate the time complexity for this one, it will almost take some 40 seconds. So we are taking very fastest computer. 2 power billion operations per second means maybe you can assume it as a supercomputer also, right? So if you operate it, then it is reduced to 40 seconds. But if you test this AKS algorithm on the normal computers, it is also going to take large time, or it is going to take very high time, right? That means it is taking longer days, or almost it will take weeks also to calculate a simple thing. So this is the reason why these two deterministic algorithms, the divisibility algorithm and the AKS algorithm, has failed. What is the reason for their failure? What is the reason? Please respond. Why this divisibility and AKS algorithm has failed?
Insufficient to find large prime numbers, sir.
the reason is the time complexity of the bit operations that these algorithms are going to take is in exponential fashion. It's a very large length of time they are taking, right? So these algorithms are not suitable for the general usage due to the length of the time required to verify the primality, right? So for this reason the probabilistic algorithms has been developed. So the deterministic algorithms failed because of the time that is taken by these algorithms is exponential. So we need to develop algorithms which take less time to compute these things. So for this reason we have probabilistic algorithms which provide much faster response times, right? Much faster response times than these deterministic algorithms. Is it clear? So there is a study saying that the AKS algorithm, which takes some hours of time to compute a particular computation, if you implement the same problem on the probabilistic methods such as the Miller-Rabin method, it will take just a few seconds. See how that difference of time is there. So these deterministic algorithms, they are taking hours of time to calculate a computation, but by using these probabilistic algorithms they are going to complete it within few seconds, right? So that is the reason why the probabilistic algorithms has been developed. So coming to the gist of all these things, the deterministic algorithms have two types of algorithms. The first one is the divisibility algorithm and the second one is the AKS algorithm. Both these algorithms failed in the primality testing of very large numbers, not small numbers. They failed in testing whether the given number is prime or not for a very large number. Why? Because the time complexity taken by this AKS algorithm and divisibility test is almost exponential. Therefore, they take some hours or weeks or days of time to compute a complex thing. For this purpose, we have entered into the probabilistic algorithms, which takes very few seconds of time to compute the things for the same complexity of the problem. Clear?
Yes, sir.
Yes, sir.
So the second part which we are going to discuss is the probabilistic algorithm, where we are going to discuss the Fermat's test, right? So the Fermat's test is the first probabilistic method we are going to discuss. In the last class, also in the last session, we have discussed a formula for the Fermat's little theorem, right? So what is that formula? Here we have given it, right? So if n is prime, a power n minus 1 is congruent to 1 mod n. So from this Fermat's little theorem only, they have developed the concept called as the Fermat's test. So Fermat's test is defined as if n is prime, then a power n minus 1 is congruent to 1 mod n. Listen carefully. Here there is a difference between this Fermat's little theorem and the Fermat's test. You can see here that a power n minus 1, this n minus 1 belongs to power exponent. But here in the Fermat test we are just changing it. If n is prime, a power n minus 1, so we have to subtract 1 from a power n, is congruent to 1 mod n. And if n is composite, it is possible that a power n minus 1 is congruent to 1 mod n. See, there is no difference between this a power n minus 1, this formula and this formula, right? But if n is prime, it is definitely satisfied. This formula, this relation is definitely satisfied. But if n is composite, then there is a possibility that this is satisfied. That is the difference you should understand, right? So by looking at these formulas, both of them appear same. But you have to observe that this particular formula holds correctly when n is prime, and this particular formula may hold or may be correct if it is composite. This is the primary difference you should understand between these two things. Clear?
Sir, yes, sir.
So that is what we are saying. Prime number passes a Fermat's test. Definitely it will pass. Passing a test is nothing but this one only. This particular formula holds. That is nothing but Fermat's test. So a power n minus 1 is congruent to 1 mod n is the Fermat test. This will definitely hold if the given number is prime. But if the given number is composite, it may pass the Fermat's test with a probability of epsilon. So that is the reason why we categorize this Fermat's test under the probabilistic algorithms. They are going to say the probability. So if n is composite, so with this probability epsilon, it is going to pass the Fermat test. That is what is saying. Is it clear?
Yes, sir.
Sir.
So again, if you consider the complexity of this Fermat test, the complexity of the Fermat test remains the same as that of the deterministic algorithms. That is, the complexity, the bit operation complexity is exponentiation in nature, similar to that of deterministic algorithms. Right? But why we are discussing means because this is the basic probability test we are going to discuss. Right? So this is the first probabilistic algorithm. That is the reason why we are discussing. But we don't have that much good results from this Fermat test. Again, the complexity is exponentiation in nature. But the next algorithm which we are going to discuss, the square root test, this also have a problem, right? They are not going to achieve our goal. What is our goal from the probabilistic algorithms? The goal is to reduce the time complexity of the operations. Since we have the exponentiation time complexity with the deterministic algorithms, our goal is to reduce the complexity with the probabilistic algorithms. But the first two algorithms from the probabilistic, that is the Fermat's test and the square root test, is failed. They are also going to fail, right? So forget about this square root test. It is also giving a formula. This is the formula, right? So if n is prime, square root of 1 mod n is equal to plus or minus 1, and if n is composite, square root of 1 mod n is equal to plus or minus 1 and some other possible values. So right, whenever we say that other possible values, this itself is saying that it is giving some probability. So this is categorized under this probabilistic algorithm, right? If it is clear, we are moving into the most important topic of our today's session, that is the Miller-Rabin test. Rabin-Miller or Miller-Rabin, anything you can call. Right, shall I proceed?
Yes, sir.
Yes, sir.
Right. So please concentrate on this Miller-Rabin test. So the importance of this Miller-Rabin test is it is going to produce an algorithm, or this algorithm gives the time complexity which is very much far better than the other algorithms. So this is our point of interest in this present session. Right. So the main purpose of this Miller-Rabin test is to test whether a number is prime or not, right? We are discussing it under the category of primality testing. So this says that whether a given number is prime or not. So this is the algorithm. Are you able to see this algorithm? It is somewhat faded. I don't know what happened to it, but are you able to see it?
Yes, sir.
Right. So you just have a look at it, and if possible you take the screenshot. I am going to explain this algorithm now. Right. So what this algorithm says is, see here, we will be given n value. N can be a large number. It can be a small number or a large number, whatever it may be, but it is just an integer. So if n is given, our aim is to check whether this is a prime or composite. Right. So first of all, what we have to do is we have to implement this formula. So we take this n and we subtract 1 from it, and that should be equalized to 2 power k into m. I will tell you with example how we can formulate this one, right? So what you will do is, if n is given, you just take n minus 1 and you divide it with this n minus 1 by 2, right? For example, okay, you just remember it. I will tell you the things while we come across the example. We divide this n minus 1 with 2, therefore we will get a result such that it is 2 power k into m, where m is an odd number and n minus 1 is even number, right? After this, we have to choose a value a. This we are calling it as base. We have to choose a base between 1 and n minus 1. Any value you can choose, but basically it is better that we start with a smaller base. We start with 2. You can also take 3, you can also take 5, like that, anything you can take. Is it clear up to these first 2 steps? When you are given a number n, you have to find n minus 1, and that should be designed, or that should be formulated in this formula 2 power k into m, where m is should be a odd number and k is something where we will use it in the next cases, right? We have to choose a base a between this 1 and n minus 1, that is, you can take 2, 3, 5 and so on, which is less than or equal to n minus 1. And the third step is you have to calculate the value of b. The b is given as a power m mod n. So a, I know, I have taken it from here, from second step, which is a base. You can take it as 2, or if the result is not satisfied, you can go for 3 also, or if it is not satisfied, you can go for 5 also. Anything you can take, but basically we will start with the base 2. And what is this m? This is an odd number where we have got from the first step. So this is from step 2 and this is from step 1. Mod n, we know what this n is. This is given by the user. So after calculating b, we have to check the condition. If b is congruent to 1 mod n, then it is simply prime number. No need to go further. So whatever b you have calculated, if it is congruent to 1 mod n, you simply return a statement saying that n is prime. But if this condition is not true, if this condition is true, then you will return this n is prime. Otherwise, you have to enter a loop, right? The loop starts from I is equal to 1 maybe, right? It's not 0. From I is equal to 1 to k minus 1. What is k? Where did I get this k? From step 1. It is nothing but power of 2. So for example, if the power of 2 is 4, so how many times I have to loop? K minus 1, 3 times I have to loop. If the power of 2 is 5, I have to loop 4 times. Like that, this loop has to be executed some k minus 1 times. And again you have to calculate the b. If b is equal to minus 1 mod n, then return n is prime. Else you have to again calculate the b value, which is equal to b is equal to b square mod n. This b is the new b you are calculating, and this b is the old b you have. So you take the square of it and mod n. Similarly, this has to be repeated k minus 1 times. After this you will return this n is composite, right? You will check for the primality whether the given number n is prime or not in these two cases. If nothing is succeeded, then you simply return that n is composite, right? I know that you will be confused with this algorithm. If you go for an example, it will be very clear, right? So shall we proceed?
Yes, sir.
Right. Here is an example of this 561. Now my primary task is to check whether 561 passes this Rabin-Miller test or not. Passing Rabin-Miller test means it will check whether it is prime or not, right? So sometimes, for example, right, let us start with it. So the first step is you have to calculate this one, that is n minus 1 is equal to 2 power k into m. This is the formula you have to use. So what is n here? What is the value of n?
561.
561, sir.
561. So if n minus 1 is taken, what is the value? It is 560, right? So how can I convert this 560 into 2 power k into m? Means you divide this 560 with 2. So it is 280. Am I right or not? And again divide this 2. It is 140. And again divide this 2. It is how much? 70. Again this divide this 2. It is 35. So I can write this 560 as 2 power, how many 2's are there? 4 into, what is the last one I have? 35. Is it clear how I can write this 560 into 2 power as a formula of 2 power k into m?
Yes, sir.
Yes, sir.
Right. So what is the value of m here? 35. What is the value of k here? 4. So how many iterations I have to perform? If k is equal to 4, I have to perform k minus 1 iterations. So if k is equal to 4, it is 3. 3 iterations I have to perform. Right. So this is step 1. And step 2, I have to select a base. Let me select the base as 2. As I told that you can take any number between 1 less than or equal to a less than or equal to n minus 1. From 1 to 560 you can take any value, but basically I will start with lower number for simpler calculations, right? So a is equal to 2. This is the base I have taken. And the third step is initialization. You have to calculate the value of b, which is given by the formula 2 power m mod n. So this is base. 2 power m means this is base, right? The base formula is b is equal to a power m mod n, where a is base. So 2 power m mod n, 2 power 35 mod, what is n here? 561. So I have to simplify this 2 power 35 mod 561. What is 2 power 35 mod 561? Any idea? Any idea? Are you able to see this open board?
Yes, sir.
Yes, sir.
Right. Now I am going to tell a very important concept which is called as modular exponentiation. Listen carefully. This is very much important for these type of calculations. So when we have the powers like a power m mod n, this is considered to be the modular exponentiation problem. Listen carefully. So how we can solve this modular exponentiation problem? For example, let us take a simple thing. We'll start with simple thing, right? If I want to calculate 3 power 10 mod 5, so 3 power 10 is something which is very large number, right? We are starting with very simple thing, but even then the 3 power 10 is a very large number. Maybe your calculator is able to calculate this value or not, that is a different case, right? So how we can simplify this particular problem is by making use of the concept called as repeated squaring. Listen carefully. Repeated squaring. Please be active. Repeated square. So for this purpose, what I have to do is, first thing you have to do is, you have to calculate 3 power 1 mod 5. What is 3 power 1 mod 5? It is 3 mod 5. What is 3 mod 5? What is the value?
3, sir.
3. Super. And second step is, you have to square the given number, right? If I square it, I get it as 3 square. Am I right or not? 3 square mod 5. So how can I write 3 square? 3 power 1 whole square mod 5. But I have the value of 3 power 1. What is the value of 3 power 1? What is the value of 3 power 1 I got?
3, sir.
3. Therefore, I can replace it. 3 square mod 5. So, what is 3 square mod 5? It is 9 mod 5. What is 9 mod 5?
4, sir.
4.
4, sir.
So, in the third step, what I will do is, I will square this one. So, if I square this one, what will I get? It is 3 power 4 mod 5. So, no need to calculate 3 power 4 value. I have already calculated the value of 3 square mod 5 as 4. So, I can write this 3 power 4 as 3 square whole square mod 5. So, it is, what is 3 square value here? 4. 4 square mod 5. So, what is 4 square? 16. What is 16 mod 5?
1, sir.
1, sir.
1, right? So, this is the basic value you will get. So, when you get 1 or minus 1, the remaining things will go with 1 only. Why? Because, for example, if I want to calculate, if I want to square this one, what will I get? 3 power 8 mod 5. Am I right or not? How can I write this 3 power 8 mod 5? 3 power 4 whole square mod 5. Right? So, what is 3 power 4? I have calculated it as 1. So, 1 square mod 5, that is equal to 1 mod 5. What is the value here?
1, sir.
1. So, what happens if I take 3 power 16? What is the value of 3 power 16 mod 5? Let us take, it is not necessary, but let us check. 3 power 16 mod 5 can be written as 3 power 8 whole square mod 5. 3 power 8 I have calculated as 1. 1 square mod 5, that is equal to 1. So, whenever you get this value as 1, from there onwards you will get the same value 1 only, right? But once you don't get this 1, you have to calculate it on your own. Is it clear up to this point?
Yes, sir. Yes, sir.
So, how you are, you may be having a doubt that how 3 power 4 is equivalent to 3 square whole square. Is there any doubt like this? So, it is generally a formula. We have seen the properties of the modular arithmetic, where a plus b mod n is equal to a mod n plus b mod n and then mod n. Like that, we have a into b mod n also. We have three properties, right, on addition, subtraction and multiplication. So we can write, you can split it like this. So 3 power 3 square whole square is nothing but 3 power 2 into 2. That's it. Is it clear? It is not 3 into 2, 2 into 2, it is 3 square whole square. Is it clear?
Yes, sir.
Now our task is to find 3 power 10 mod 5. But I have calculated, I have the values of 3 power 1, which is 3, 3 square is 4, 3 power 4 is 1, 3 power 8 is 1. Now what is the combination of 10 from these two powers? Right. For example, let us take 12. What is the binary combination of this one? 1 1 0 0. Am I right or not? This is 8, this is 4, this is 2 and this is 1. So if I want to get 12, I have to add these two, therefore I will set it. So 1 1 0 0. How can I get 13? What is the binary combination of 13?
1101, sir.
1101, right. So like that, if I want to have 10, what is that? I can write it as 3 power 8 plus 2. Shall I write it like this?
Yes, sir.
So 3 power 10 mod 5 can be written as 3 power 8 plus 2 mod 5. So what is 3 power a plus b? How can I write exponentiation? 3 power a plus b, I can write it as 3 power a into 3 power b. So I write it as 3 power 8 mod 5 into 3 square mod 5. This is the third property of the modular arithmetic, and mod 5. So what is 3 power 8 mod 5? What is the value I got here?
1, sir.
1
sir.
into, what is the 3 square mod I got? 4.
4.
So 1 into 4 mod 5, which is nothing but 4 mod 5, which is equal to 4. So 3 power 10 mod 5 is nothing but 4. This is how we have to calculate. Is it clear?
Yes, sir.
Right. So this is a very simple example I have taken. So shall we do another thing?
Yes, sir.
So what is the value of 3 power 200 mod 50? 3 power 200 is a very large number, right? Even the computer or the calculator cannot calculate it. It will simply say that stack overflow. So for this we have the repeated squaring method, where I have to first find 3 power 1 mod 50. What is 3 power 1 mod 50?
3, sir.
3, sir.
3. Now I square it. 3 square mod 50, which is nothing but 3 power 1, I know 3, right? What is 3 square? It can be written as 3 power 1 whole square mod 50, that is equal to 3 square mod 50, that is equal to 9 mod 50. So what is the value? It is 9, right? Now I square this one, so I get 3 power 4 mod 50 is equal to 3 square whole square mod 50, that is, what is the value of 3 square here?
9, sir.
9 square mod 50, that is equal to 81 mod 50. What is 81 mod 50?
31, sir.
Super, 31. Now again I will calculate. So I have to calculate 200, right? Power of 200. So how can I write the combination of 200? Any idea? What combination I have to take to get 200? Binary equivalent. This is 1, 2, place value I am writing 8, 16, 32, 64, 128. Shall I need to take 264 also? 256? No, right? Why? Because 256 is a power which is greater than 200. So we have to consider the powers up to less than 200 only. Right? So out of these things, what combination makes 200? 200 is given by 128 plus 64 plus 8. So what is 128 plus 8? It is 136. 136 plus 64, it is 200. So I have to get the value of 3 power 128, I have to get the value of 3 power 64, and I have to get the value of 3 power 8. Remaining things is not important. So these three values I have to get. So I have to check up to 3 power 128. Right, now tell me, what is the next thing I have to do? You have to square it. If I square it, what will I get? Squaring means you multiply it with 2.
8, sir.
8. 3 power 8 mod 50 is equal to 3 power 4 whole square mod 50, that is equal to 31 whole square mod 50. What is 31 whole square? You can take the calculator, it's not an issue. It is 961 mod 50. So what is 961 mod 50? So 961 mod 50 means 50 goes to 950 exactly up to 950, so the remainder is 11. Now I have to calculate 3 power 16 mod 50. So what is 3 power 16? I can write it as 3 power 8 whole square mod 50 is equal to, what is 3 power 8? 11. 11 square mod 50, that is equal to 121 mod 50. So what is 121 mod 50? 21.
21, sir.
Now 3 power 32 mod 50. It is 3 power 16 whole square mod 50. I know that 3 power 16 is 21 whole square mod 50. What is 21 whole square? 20 20 is 400, 441, right? 441 mod 50. So what is the value of 441 mod 50?
41, sir.
41.
41, sir.
Super. Now I calculate 3 power 64 mod 50. I get it as 3 power 32 whole square mod 50, which is equivalent to 41 whole square mod 50. So 41 into 41 means 40 40 1600.
1681, sir.
1681. Super. 1681 mod 50. So what is the output I will get?
31, sir.
31, sir.
Super. Now the last step, 3 power 128 mod 50, that is equal to 3 power 64 whole square mod 50, that is equal to 31 whole square mod 50. What is 31 whole square? 961
960.
mod 50, that is equal to 11. Am I right or not?
Yes, sir.
So I can write this 3 power 200 as 3 power 128 plus 64 plus 8. That is 3 power 128 into 3 power 64 into 3 power 8 whole mod 50. What is 3 power 128 mod 50? 11, right? 11 star. What is 3 power 64? 31 star. What is 3 power 8? 11 whole mod 50. So 121 into 31 mod 50. What is 121 into 31? What is 121?
3751.
What is that value?
3751.
3751 mod 50. So what is the value I got here?
1, sir.
Only 1.
One, sir.
Super. So this is how we need to calculate these exponentiation values. Clear?
Yes, sir.
We'll see some examples on the same thing from in the next session, but let us continue with the same example from the Rabin Miller, right? So the Rabin Miller, this after completing this example, we'll just close the session and we'll continue with the same thing in the next class. Why? Because it will not be completed by today, right? So is it clear? So 2 power 35 mod 561. Now we'll calculate this one. So my task is 2 power 35 mod 561, right? So how can I solve this one? 2 power 35 means, how can I write it? 2 power 35 means binary equivalent. Please respond. How can I write 35? Combination of two powers. It is 2 power take this one 2 4 1 2 4 8 16 32. Shall I take 64 also?
Yes, sir.
Shall I take 64 or is it not? It is not necessary. What is the combination of 35? What bits I have to set? If I take 64, is it good or not?
10011, sir.
No. So this is the bit combination I have. The place values are 1, 2, 4, 8, 16 and 32. Shall I take 64 also? Or it is not necessary?
Not necessary, sir.
It is not necessary. Why? Because my power is 35 only. So from these combinations I have to check whether I will get that 35 or not. So how can I get 35? 32 plus 2 plus 1. Am I right or not? So 32 plus 2 is 34, plus 1 is 35. So I have to calculate the values of 2 power 32 mod 561, 2 power 2 mod 561 and 2 power 1 mod 561. So I can write it as 32 plus 2 plus 1. Now I will start with this repeated squaring. 2 power 1 mod 561. What is the value of 2 power 1 mod 561?
2, sir.
2, sir.
2. Now 2 square mod 561 is given as 2 power 1 whole square mod 561. I know that 2 power 1 mod 561 is 2, therefore 2 square mod 561. Tell me the value. 4 mod 561. It is equal to 4.
4, sir.
Next 2 power 4 I have to calculate. 2 power 4 mod 561. That is 4 square. Am I right or not? So I know this 2 square whole square. 2 square whole square mod 561, that is equal to 4 square mod 561, that is equal to 16 mod 561, that is equal to 16. Next 2 power 8 mod 561. How can I write 2 power 8 mod 561? 2 power 4 whole square mod 561. That is equal to 16 square mod 561. What is 16 square?
256, sir.
Super. Right, it is 256 mod 561. What is the value? It is 256. Right. Now I calculate 2 power 16 mod 561. What is 2 power 16? I can write it as 2 power 8 whole square mod 561, that is equal to 256 whole square mod 561. What is 256 whole square?
65536.
What is the value?
65536, sir.
536 mod 561. What is the value? You can use the calculators also. I don't have the calculator.
Sir.
What is the value? Last few minutes. Two 56 start 256 mod 561. So I am getting 460, right?
Sir.
Rajesh, I can understand, but last 5 minutes.
Okay, sir.
It is 460. Now 2 power 32 mod 561, that is equal to 2 power 16 whole square mod 561, 460 whole square mod 561. Tell me what is the value? 460 into 460 mod 561 will get 103. Now I have to calculate 2 power 35 mod 561. It is 103 into, what is 2 power 8? 256 into, not 2 power 8, right? It is 2 power 32 into 2 square into 4 into 1, that is 2. So 103 into 8 mod 561. You will get the same answer here. So you will get 263. So once you calculate the value of b, this is not equal to 1, right? If it is 1, then you can simply say that the given number n is prime. Therefore you have to enter into the loop. So I take the value of k is equal to 1, b is equal to b square mod n. So I calculate the new b with the old b. What is old b? It is 263. So 263 whole square mod 561. It is 166 mod 561. That is 166 I got. Now I take the value of k. Calculate new b with the previous b. So it is 166 whole square mod 561. It is 67. Now for the third iteration k is equal to 3, I take b is equal to b square mod n. So 67 whole square mod 561, which is 1. So when I get 1, I get, here I should get as minus 1, right? But I got it as 1. So finally the output is a composite. So whatever number you have given, that is 561, is a composite number. So is it clear how to calculate this Rabin-Miller algorithm?
Yes, sir.
Right. So by this we'll just put an end to today's session, and we'll discuss the remaining examples in this Rabin-Miller and the recommended primality test in the next session. So that's all for today's session. Thank you one and all for joining the session.
Thank you, sir.